I had a lot of fun putting exercise 10 together for you, and I hope you also enjoy working through it and also learning about linear algebra and some of the difficulties, some of the numerical challenges that arise with computer linear algebra or digital linear algebra. Okay, so using the Hilbert matrix function, and you can use either the function that you wrote in the previous exercise, or you can use the SciPy Hilbert function that is built in. Create a Hilbert matrix, compute its inverse using linalg.inf. Now, we already did this in the previous exercise, and compute the product of the two matrices. Now, that product should equal the identity matrix, which means if you compute the Euclidean distance between the Hilbert matrix times its inverse on the one hand, and the identity matrix produced by numpy.i on the other hand, that difference should be 0, right? If both of these matrices are giving us the identity matrix, the Euclidean distance between them should be 0. And well, if the Hilbert matrix times its explicitly computed inverse is not the identity matrix, then the Euclidean distance is going to be something other than 0. Okay, compute that Euclidean distance, and then take the code that you wrote here put it into a for loop to range from matrix sizes going from 3 by 3 Hilbert matrix to a 12 by 12 Hilbert matrix. Now, keep in mind that a 12 by 12 matrix is, if you're doing linear algebra computations like the inverse by hand, a 12 by 12 matrix is a total nightmare. But for applied linear algebra, 12 by 12 is really small. That's really not a very big matrix. Okay, so for each matrix size, compute and store the Euclidean distance between the Hilbert matrix times its inverse and the identity matrix that comes from NumPy, and also compute the condition number of the Hilbert matrix. Now, condition number is a quantity that I have mentioned already a few times earlier in the book. You will learn exactly what it is and exactly how to compute it and exactly how to interpret it later in the book in the chapter on the singular value decomposition. But essentially, a condition number is a measure of the spread of the values in a matrix. If a matrix has a small condition number, so closer to 1, then it means that the matrix is kind of more contained. The numerical values in the matrix all have roughly the same magnitude, the same numerical size. Okay, and you can use numpy.linalg.cond to compute the condition number of a matrix. Okay, so all of this stuff that I just explained, you then want to repeat that using random numbers drawn from a Gaussian distribution, but everything else is the same. Okay, and then you're going to generate a plot that looks something like this. These are Euclidean distances in log space on the y-axis and the matrix size on the x-axis. I'm going to interpret these results more when I produce them in Python. So here we have our matrix sizes, and these are the matrices where I'm going to store the results. So I call this the identity error, but it's the Euclidean distance of the matrix times its transpose versus the identity matrix. And it's 2 over here because we do this for the Hilbert matrix and for the random numbers matrix. Okay, so here we have a loop over all the elements in this array here, matrix sizes. Here we compute the k by k Hilbert matrix, compute its inverse, compute its the matrix times the inverse, which should be the identity matrix. Here I call this the error matrix, that is this matrix product here, which should be the identity matrix, minus the identity matrix given by the I function. And of course, you could also just create this as a diagonal matrix with ones in the diagonal. Here you see I'm computing the Euclidean distance, so I square all the elements in the error matrix, sum them up, and take the square root, and then I compute the condition number. Now, this code here is identical. I even kept the variable names the same. The only difference is that instead of using the hilbmat function, I'm using numpy.random.randn. Okay, otherwise it's the same. Okay, well, except for the indexing here, of course. All right, and then I make this plot. Okay, so what is this plot showing? So this is the distance to the identity matrix. Now, in theory, all of these distances should be 0. So in fact, when I compute the log, you can see here's where I'm in the plotting code, I'm computing the log. Now, if all of these numbers are 0, which they should be in theory, so the matrix times its inverse is the identity matrix. So identity matrix minus the identity matrix should be the matrix of all zeros. Euclidean distance of all zeros should be 0. And then you take the log of 0, that's not a real number. So in fact, we should be getting, in theory, we expect to get lots of Python error messages and warning messages saying that we are computing the log of 0, which does not exist. So it's already noteworthy to see that there are no error messages or warning messages, which tells us that even for the random numbers matrix, the matrix times its inverse is not exactly the identity matrix. It's going to be some tiny, tiny number. You can see that the log of that number is minus 35. So this is a really, really small number, but it's a little bit above 0. And, that's just numerical inaccuracies and rounding errors when it comes to computing the matrix inverse. Okay, but the important thing to notice is that for a random numbers matrix, that distance to the identity matrix is small, but it's consistently small. It's, basically minus 35, regardless of the size, at least going up to 12 by 12 matrices. But the Hilbert matrix, on the other hand, has this almost perfect linear relationship in log space, which means it's actually an exponential relationship. So the distance to the identity matrix, or the error from the true identity matrix, is actually growing exponentially. It's linear. It appears linear because I'm computing the log of the distance. So in a linear space, this is exponential growth. So that is nightmarish, right? That is terrifying. That means that there's huge errors when computing the Hilbert matrix times its inverse, and that should be the identity matrix. Okay, and then this is a complementary plot. This is showing the condition number. Again, it's the log of the condition number. This should be pretty stable. There's no value that it needs to take on for the random numbers, but they should be relatively small, indicating a stable matrix. And you can see as well, the Hilbert matrix is just growing. Okay, now the last thing I want to do here is just get rid of this log, just to show you what the growth really looks like. I'm just using log here to facilitate visual inspection so you can see all of the numbers on the same thing. Okay, so here, look how fast it's growing. It's literally exponential growth of the error. And here is the condition number. Look at this. This is 10 to the 16. It's a very, very large number, and this is only a 12 by 12 matrix. The last thing I want to mention in this exercise in this video is something that I mentioned earlier in the book, probably in chapter 1 and maybe chapter 2. And that is that I don't want you to see these exercises as just tedious homework that you have to do. Instead, I hope you use these exercises as inspiration and starting points for continuing to explore linear algebra using code on your own. I tried to design these exercises to have enough diversity that they will allow you to get started. I really believe that the best way to learn concepts in math, and in particular applied mathematics, is to implement them in code. Use your sense of adventure and your creativity and curiosity to continue exploring linear algebra in Python.